Before I start, I think I'll just mention a little bit about what Michael was just talking about. He said there were a lot of interesting technical problems that they solved, and I'm sure there were. There were also some interesting human problems, and I think those were something I'd like to address just a bit, and that is that the team that originally developed this application did so in MATLAB, as Michael mentioned. And MATLAB had a module that let them generate C code. So they were able to actually generate C code and run it and demonstrate it. And then we ported the thing, or started to port it. And we ran into some problems, which were communication issues. It was really hard to get information out of these people. You'd ask them how this thing works.
It's magic.
Yeah, it's kind of, well, it works. We tweaked it. We tweaked it until it works. Well, what does it do? Well, it works. I mean, this is kind of what it was like, and it was really hard to get from this MATLAB abstracted view of this thing to a hard, understanding of what it was really doing, and then be able to fit it onto the processor. So I'm very impressed with the work that's been done on this project. And it is quite fascinating project. The algorithms that are used are very counterintuitive. The research on how hearing degrades and how it is restored is counterintuitive. It doesn't work the way you would have thought that it would work. And there were some really interesting people working on this project, but getting from their expertise into Forth and the Forth chip was quite a challenge. So Michael didn't talk about that, but I think that's a very interesting aspect of the work. And in fact, I'd say that this last year I haven't been as deeply involved down in the trenches, in the bits, fighting the bits and getting the projects done one at a time and working on the technical stuff. And that's given me a little of an opportunity to step back and look at things from a little more abstracted, distant view. And that's been kind of fun to look at some stuff. So I thought I'd just review a little of the stuff that I put in my blog this last year. I came down and did a presentation here on the green array pulse width modulation code and the IDE in ColorForth, and I'm going to follow up on that today. One of the things I was looking at earlier in the year was the aspect of language syntax. As you know, Forth doesn't have much. A lot of other languages do, and a lot of what's involved in working with those languages is fitting your problem into the syntax of the language. And what makes Forth somewhat different is that we adapt the syntax of the language to the problem, rather than having to shoehorn problems into our syntax, because we have so little syntax and we can adjust it. But to me, this brought up a more interesting issue, which is about language itself. I saw some fascinating research about the relationship between language and other mental activities, and how scientists have demonstrated that by suppressing our language processing in our brains, we can accelerate functions that take place in other parts of our brains that are suppressed by our focus on language. If you've ever studied martial arts, this is something you've probably been exposed to, because using language at the wrong time can get you killed. I say it's kind of like somebody trying to text while they're driving their car. And this happens a lot. And it doesn't happen to us as much in Forth because we aren't as limited by the language aspect of Forth. Forth is more than syntax. It's more than just a programming language. It's a system for solving problems. And a lot of the mental activity that takes place when you're working on Forth isn't language-oriented. So I think that's something that, it's an interesting subject. I did some follow-up on it and wrote an essay about the differences between the kind of activities that take place in our brains. A lot of people work with languages that are very left-brain oriented, and they have a very hard time understanding what we do at Forth, because we are not entirely left brain oriented. We're not just shoving problems into the fixed syntax of our language. We have bigger boxes we can work with. One of the things I did, I posted some details on the presentation I did last year. I showed you how we could take objects from a library and drop them onto a picture of our chip and generate code templates and actually generate code. I used the example of the talking voltmeter that took in an analog signal, linearized it, converted it to digits, looked up those in a little SPI sound player, split the output of the sound player to a couple buffers and played it out either on a digital pin or an analog pin, and this talking voltmeter took about 150 bytes of code. But more importantly was the approach, which was that based upon using these templates, and again here was the code that generated the application, basically just including little modules and showing how they are connected up to one another, and all of that information is expressed graphically in this image. So that was just a little follow-up. I put that information. I also put that paper that I had talked about, the one with the long name, the Transformational Algebra for Communicating Sequential Process Data Flow Diagram Statements in Classes of Parallel Forthlet Objects for Design, Automated Place and Route and Application Development on Seaforth Architecture. And I put that on the web so anybody that wanted to look at the documentation that went with the presentation could go with it. Occasionally I read com.lang.forth, and occasionally they talk about me or things I've written, and one of them came up was, well, don't you remember Jeff Fox's horror stories about coding at ITV? And I thought, well, you know, people miss the point of these things. The point wasn't the horror story. The point was how the code was made better. Not that the code in the library was a piece of crap, but that we improved the code that we took out of the library. And that's what people are supposed to learn from these stories. And I followed up on that a little bit later. What I had really talked about was the changes to the hardware, and this is probably what you're interested in. Green Arrays has been working on new chips, the GA32, the 32 with 5-volt I/O, a GI40, a GA4, and a GA144. And the GA4 is obviously the smallest. It's just got 4 cores, so they're all corners. They only have 2 neighbors each. It's been put into a couple of different packages. One of them is very small. Well, they're both very small. One of them doesn't have the connection for the SPI on it. One of the things that we did with this chip is that we're distributing it. Now, we no longer have to have one chip with, say, if you need 40 cores, one chip with 40 cores, and then run your I/O out to wherever it needs to go. Now you can distribute your intelligence and put some of your cores out there where the pins are that you need to use them, and distribute your system. So we put some serial communication code in the GA4 that was new. We had asynchronous code, and we put that in, but we also put in some pulse width modulated code. And this was new code. It's like one-wire code, but one wire refers to a particular protocol that is sort of industry standard, and really I like to call this pulse width modulation serial code. The important thing on this code was that we had always had ports on the chip that we could read. But the ports that had our wake-up function, the pin ports, we had to read those as a data statement to use the wake-up feature. So you read the port that has the pins on it, you go to sleep. When the pin changes, you wake up. And when you wake up, you read garbage. Because the hardware connected the handshake from that pin as if it were a handshake from a neighbor communication port. but there is no neighbor communication port. So if you read if you're in a corner of the chip and you read your left port, there's no neighbor there. But a pin is connected to that circuit such that a change on that pin will provide you a wake-up, and you can wake up from this read and process the event on the pin. In the process of doing that, you read garbage, because there is no port connected to this circuit. So on all the previous chips, the way this worked was you would say, go to sleep, wake up, throw away the stuff you read when you woke up, and look to see whether you were awakened by a pin or by a neighbor. Okay? Now, if you were awakened by a neighbor, you process the stream of data coming from your neighbor. If you were awakened by the pin, then you jump to the code to process the signal on the pin, like asynchronous bit bang, synchronous bit bang, pulse width modulation bit bang, some kind of SPI bit bang. You wake up to process your pin. And as a result of this, we needed code which would read the port as a data statement and determine whether it was really a pin or a port that woke you up, and then you could go execute a multi-port address if it was a port that woke you up, or you could go execute ROM code if it was the pin that woke you up. Well, Chuck decided that it would be a good idea to change the hardware such that when you read a port, when you read one of these ports where there's nobody there, there's no neighbor, but there's a handshake wake-up, let's read something useful. Let's read data. Let's have the hardware put some data on the bus so we know what we're going to read. We're not just going to read garbage. We're not going to read just what used to be on the bus. We're going to put a little circuit in there so that when this wake-up circuit wakes you up from reading this port, you'll read something known. And the thing you'll read is an instruction. And the reason why it's useful to read an instruction is because now you can read this port with your program counter. Because now when you wake up from the read, you're reading something useful, an instruction which you can execute. Previously, we had to read this port as a data statement because you couldn't read garbage and feed that in to your program counter for execution, or there's no telling what would happen. So this simplified our code because now we didn't need one section of code to process the multi-port address wake up and another section of code to process the pin address wake up. We could kind of mash these two things together, and it made our code shorter. Now the asynchronous bit bang code is also auto-baud. So it actually times bits and determines some baud rate between 1200 baud and a megabaud, a couple megabaud to run it. And that makes it a little more complicated. Asynchronous code at a fixed baud rate is shorter, but the pulse width modulation code that we did for GA4 was the shortest serial routine we had done yet. And Chuck wrote a version, and then I wrote a version, and mine was very close to Chuck's. I made some very small changes to mine based on what I had learned from what Chuck had done. And here's some code, some color-forth code. And I showed this last time I was here. And I find it fascinating. There's not much code, but it does a lot. This is the boot code for the GA4, an early prototype. This code's already obsolete. There's been new hardware changes since then, and this code has been updated. But I'll review it again for those of you who were not here for my last presentation. What this code does is initializes the registers by putting the address of the I/O register into the B register. And then it calls a routine called receive to receive a word from the thing that's transmitting it. And receive puts 17 on the stack. It duplicates that, so it uses that as a counter for 18 bits. So we have a number that we are going to shift 18 bits into. We call a multi-port address RDL-. This goes to sleep, will be awakened by a message from the right port, the down port, or from the pin on the left port. If we're awakened by the pin on the left port, we're going to read the sequence fetch, B, return. That's the code that the hardware is going to feed to the processor to read. So if we get awakened by this pin changing, then it's going to execute fetch, B, return from that port. So it's going to read the value from the pin with the fetch B, and it's going to return. Then we test the most significant bit to see whether the pin was high or low with a dash if. From there, we have two next loops. But you notice that we split them so that we have for, begin, if, and then two nexts. So we've merged the nexts into the if statement. We have one dash if and two phrases. If the bit is high, then we drop it, we shift a 1 bit into the least significant bit of the word by doing an invert, 2 times an invert, and X next means swap the two arguments on the stack because we had a begin and an if, and we want to process the begin, not the if, so we swap the two arguments and we do the next and a return, and then we do the then, which processes the if, and now the phrase for if there was a 0, then we're going to shift a 0 into the word with just a 2 times next. Okay, so that's going to wake up 18 times if 18 bits come in on the pin, and it's going to wake up when the pin goes high, and then it's going to read the pin a second time. If the pin is still high, it's going to get a 1. If the pin is low, it's going to get a 0. So it's measuring the width of that pulse. And it's going to do that 18 times. It's going to end up with 18 bits. And it's going to return with a word with 18 bits in it. So we read our first word, and that is the beginning of our boot packet. That is our destination address. I'm sorry, that's our execution address, and we push that to the return stack. We read another word. This is our load address. We put that in the A register. We read another word. That's our packet count. We use it for a for next loop, and in that loop we receive a word. We store that word and increment it. We loop, and when we're done, we return to the execution address that we pushed at the beginning of the packet. This is very similar to the boot code in the other chips that do asynchronous protocol boot or synchronous protocol boot. They receive a packet in this format and they load it and boot it. But we've done this with considerably less code now, and it's considerably faster. It's less code partially because this also processes messages from a neighbor. If a neighbor sends us a word, we're asleep, we wake up, we execute the whole stream from the neighbor. We don't need separate code to do that. So this was the code. This runs at about 31 megabits per second, which is pretty fast. It distinguishes between a 4.7 nanosecond pulse and an 11.5 nanosecond pulse. And it's kind of hard to generate those pulses without something pretty fast like one of our chips. So when we tested this, I took a GA32 and a GA4 and hooked them up to the interactive debugger interface and talked to them like they were two interactive force systems. And I had this one run the pulse width modulation boot code output, and I ran it out of a pin, and I ran it into the pulse width modulation boot code packet boot input on the GA4 and loaded a program and ran it. And then I ran variations with this process, both with a direct connect and with a capacitive connection between these systems to simulate them operating with electrical isolation. Now, I find this code quite fascinating because it's an example of highly factored code. It also shows what Chuck did with splitting this for next loop by adding another begin and having two nexts. And again, I like this. I think it's good to show this to the public so people can appreciate it. I've seen a lot of people who say they factor their code, but I've seen people who in comp.lang.forth say, oh, I factor my code, but when they see an example of how Chuck factors code, they've said things like they want to run away screaming. And again, this is a little more factoring than you're used to. But I challenge you to go pick a processor and write code that does this. Okay? You could do it, most anything. Take an ARM. Take your parallel ports on an ARM. Hook up the things where it's talking to 3 other computers. Have it go into low power mode. If a message comes in on one of the parallel ports, wake up and process a stream of instructions from that processor. If a pin changes on another port, wake up and process a bit-bang serial protocol code. Load a packet with an address. Also support the ability to load packets of code and pass them on to other computers. And when you finish this process, tell me if it took you more than 18 words of code for the whole thing. And I'm willing to bet that it will take you more and that it's not going to run at 31 megabits per second. Since I showed this code, I realized that there's a possible improvement in the code. You probably can all see it. I'm sure some of you can. It's the kind of thing that, you look at it for a while and pretty soon it just kind of jumps out at you. Oh, wait, how did I miss that? This routine is shifting 18 bits into a word. It doesn't matter what 18 bits are in that word before you shift 18 bits in. So, it doesn't matter what's on the stack when we duplicate it. We're just creating a space on the stack for the word that we're going to return at the end of the code. And then we put our loop counter here, 17. If you're familiar with this processor, you know this will compile a push and end the word alignment. So we have defined a word here which says dupe, literal 17, push, no op. And then the next word would be a 17. Okay? Well, prefetch starts after the last memory operation, and this is a memory operation. So prefetch would start right here. So we would load a dupe, then we would load a memory literal, and when we're done with that, we would begin loading the next opcode over here while we did the push, and then we would wait for this memory cycle to finish, and then we would go execute that opcode. And we can speed this up by an entire instruction length by swapping the 17 and the dupe. By putting the 17 here, we start the prefetch in the dupe. So we get 1.5 more nanoseconds of prefetch, and the routine takes 1.5 nanoseconds less to execute these first 2 words. And it doesn't matter, again, whether we just put garbage in there or whether we put 17 in there. We're going to shift 18 bits into that word, so it really doesn't matter what's in there. And we get a little bit of an improvement by doing that. When I originally wrote this, I also wrote more code. I wrote yellow swap, green next, the equivalent of a ANSI forth, left bracket swap, right bracket, compile next. And then I looked at Chuck's code and I saw X next, and I said, pretty obvious what he's doing. He's simplified his code by having one word that means swap the arguments on the stack and then compile a next. So I used his syntax because it was shorter and cleaner and sweeter. Oh yes. Can you see the blue words in your mind's eye? Okay, there's blue words there. Blue words are a new thing in ColorForth this last year. ColorForth always used to wrap. So how come there's not a red word at the beginning of this line? How come drop starts there instead of there? And the answer is because there's a carriage return right there. It's blue. You can't see it. That's one of the things blue words are used for. They execute when you're editing the screen. There's a switch to make them visible or invisible. It's obviously turned off right now. They're invisible, but you can still see it. because you know this drop wouldn't be here if there hadn't been a carriage return after that if to make this formatting the way it does, just to make it a little more readable. That's all. It's got a carriage return in there. But we did learn that having indents and carriage returns and BR and no carriage return did help make Colorforth more readable, being able to format it on the screen. But that's not the only thing that blue words are good for, formatting things. Another thing that they're good for is embedding executable code into your source code, which is a very powerful thing. Will Baden talked about that a few years ago, how he could cut and paste in his editor, insert a fourth phrase, pull data out of a document, execute fourth code against that data, and then do all of this from inside of the editor. But it was pretty involved, what he had to do that. And what Chuck has done is really simple. Partially because the editor is integrated in at a low level in Colorforth, and partially that was his intention, to make it simple. So he just assigned a new color, blue, and blue words execute at edit time. Okay. Let's see, what am I doing here? One of the subjects I've talked about a number of times, going back to ITV, was structures in Forth. We had structures in the ITV code used for a number of things. We had them in the GUI, and we had them in the network code. Now, the network code came from C. It was modeled on C. It was copied from C. It was factored the same way as C. It had the same names as C, the same files, structures as C. It was really the same thing. So it used structures as defined in the Forth Scientific Library, which at the time had a number of problems. And as a result of our using them, we got that code cleaned up and it was greatly improved. But nonetheless, I've always felt it was a strong example because the subject of structures often comes up. And in, say, comp.lang.forth, and almost always gets the same answer, which is, oh, well, we can do structures. Here's how we did it 25, 30 years ago at Forth Inc., and here's a way to do it. You just give names to an offset from your base, and this field is this far from the base, and that field is this far. And yes, that's a good thing to tell beginners. But I always wince at the fact that we never seem to go beyond telling beginners what to do with structures. We don't say to them, we don't have structures in the core of Forth for the same reason we don't have arrays in the core of Forth. There's not one way to do them. There's different ways to do them in different circumstances, and we do it the best way that's appropriate. So I like to use the example of what I did in the GUI at ITV. Yes, I had structures in the GUI, and they were used in places where it was appropriate to use them because the code was called so infrequently that it meant so little to the performance of the application that doing an offset calculation for every field in the structure was acceptable. But when I profiled the stuff in the GUI, there were two functions that represented 99% of the time the operating system spent calling the GUI. So that's what I focused on optimizing, was the functions that took up 99% of the GUI time. And I rearranged the fields in the structure a number of times until I got them arranged to where 9 out of the 10 field offset calculations were gone. They were eliminated. 90% of the base plus offset calculations weren't used because I was simply using the auto increment instructions that Chuck introduced 25 years ago. Okay, again, Chuck split the old fetch and store atoms to offer the power of modern computers having auto-increment instruction sets. So in these two routines that read 10 fields from the GUI structure, the naive code has 14 offset calculations, because each of these is an offset from a user variable, and then this field is this far, and this field. Well, by using the auto-increment instructions, I eliminated 12 of the 14, something like that. So again, this is my idea of how you would optimize the code. Is, you don't institutionalize the overhead, you eliminate the overhead you don't need. So it's fine to say to beginners, yes, this is the naive way of doing structures, but if you're going to be doing more advanced programming, one way of doing structures isn't going to always suffice. And sometimes you want the ability to drop in below the abstracted level of your structure code and manipulate them at a lower level where it's more efficient. So again, I gave some examples of that in my blog and showed how this kind of optimization takes place with structures in Forth, not just the things that beginners always get shown. And I was following up on that blog, and in fact, here's the example code right here. The example I used was, I said, okay, let's just take 5 fields and show an example where we read 5 items, add them together, and store it back. So we'll describe function 1 as x1 fetch, x2 fetch plus x3 fetch plus x4 fetch plus x5 fetch plus x5 store, return. Now x5, these x fields are in this application connected to a user variable, so the code they would actually compile is the user variable win for a window, fetch, and then 0 cells plus, win at 1 cells plus. Okay, so this is the kind of code you're going to get from a threaded Forth compiler. And that's the kind of code that we had in the GUI from the high-level structure code. And it was replaced with lower-level code which looked like that. Define fun1, win at, a store, fetch a plus, fetch a plus plus, fetch a plus plus, fetch a plus plus, fetch a plus, store a, return. And there's roughly a 10-to-1 relationship here between the optimized structure code and the non-optimized structure code. So again, I was looking at this code and following up. The subject had come up because Chuck has a page called 1%.html, in which he explains very well his comment that Forth should be 1% the size of C. And he gives all these reasons of why C is typically much larger than it needs to be. And we all know that, yes, C can be made small if you work at it, relatively speaking, not to the extent Forth can, but compared to what you find in standard libraries. But the point being that most people are just going to go to the standard library and paste the big bloated thing in there, and it's going to be 100 times bigger than what you could have. And, I was looking at his code, and I was looking at his essay, and I said, there's a section in here I really like called What's Wrong with C Programs? And I just took that, and I went through it, and I said, let's apply that to Forth, folks. If this is what's wrong with C programs, don't do it in your Forth programs. So I'll invite you to go take a look at that. Okay, and I'd like to follow up on that a little bit with comments here about the IDE in ColorForth. Okay, I didn't write it; it's not my code, but it's beautiful stuff. I really like it, and I think it serves a good example because it's so different than the kind of things I worked on long ago. Whenever I had to write a target compiler, and I've written a lot of them, about the first thing you do is you define your word lists. You've got to have dupe has to exist in your normal dictionary, and dupe also has to exist in your target dictionary, and dupe also should exist in an executable target dictionary, and dupe might also exist and it kind of can get complicated. And the reason you do this is so that you can mix and match everything at any time. You can write code that takes the dupe from your target compiler and the dupe from forth and the dupe from here and uses them all in the same definition. It's a powerful thing. But that's not the way Chuck does it. I mean, the first time I saw Chuck write one of these cross compilers for one of the chips, I was kind of horrified because mine was 20K and his was a half K, you know? Why is mine so much more complicated than his? Well, not only did I write much more code than I needed to for the individual defining, you know, the opcodes and the instructions because I didn't factor it well, but I also had started out with different word lists to separate the different components so that I could mix them and match them freely. And I don't see Chuck doing that. What I see Chuck typically doing is he compiles them in a certain order. And he knows what he's going to compile, what order he's going to compile them in, so he doesn't need to mix the dupe from here with the dupe from here with the dupe from here. And so he doesn't have a separate word list for the target compiler, and he doesn't have a separate word list for the IDE. And there is a conflict, but it doesn't get in your way. Makes things simple. I didn't realize I'm all the way at the end here. I brought in an old board from Intelisys. This board was one of the boards designed for the 40.
John, set up while you're wrapping up.
I can do this about 2 seconds. There have been a lot of these boards made, and they all had different features. And let me just, for a moment, say that one of the things that Green Array has done is to use the same pinout on the GA32 as the S40. So I just popped this socket, took out the S40, put the GA32 in here, and used this board. So it's a nice test board for testing that particular chip. It's a bit of an overkill. Like many of the boards Intelisys made, Intelisys bought a company that made USB chips. And they put one of these chips on to some of their boards as the interface to the PC, like on the thumb drive. So the thumb drive is talking to a USB chip from a proprietary company with a proprietary CPU inside of it with proprietary programming. And one of the functions in this chip to access the SCSI function has been taken over and reprogrammed to translate the incoming data from your PC into a synchronous serial signal, which then goes out and talks to the C4 chip. So this is that kludgy interface that he was talking about that makes it so hard when you have to go through this extra chip with the SCSI interface and the USB and deal with all of that, and then have it translate to talk to the C4 chip. It's kind of ugly. And one of the things we're working on is to have the C4 talk USB so we can just plug the C4 in with a resistor, and we don't need this extra chip that costs much more than a C4 chip, and it's ugly anyway. And that'll make it easy for us to make little devices. But anyway, you plug this in. It's recognized by the IDE. The IDE has a screen which is just a block, but it's got some blue words in it that allow it to put a dump on the screen, display the stack on the screen, and you basically pick a node on the chip, set up a path to it, and you talk to it as if it's got a fourth running on it. It uses no ROM code, it uses no RAM code, and yet you can talk to it, you can probe memory, you can dump memory, you can dump the stack, you can download programs and execute them. And it's really, really handy for debugging. So I'm running a little late. I'm not going to show it, but if you want to see it running, I'll show you the IDE here talking to the C4 chip, and you can interactively talk to a chip with what has to be the smallest fourth interpreter running on that chip of 0 bytes of RAM and 0 bytes of ROM. Thank you very much.